It is a pleasure to introduce the last speaker of the day. Is Jessica Jaurez, who will talk on formal rigidity for germ or foliation in the real plane.
Thank you. Thank you all for being here today. I am going to talk about formal rigidity for germs of smooth and real analytic foliation in the real plane. And there are two known formal rigidity results. Poincaré-Dulac and chain theorems. Which are formal rigidity results for germs with linear particles, germs of Pepe Seade. Here we have linear particles. And the purpose of this talk is to answer the following question. Are there analogous for Poincaré and chain theorems for degenerate singularities? In the real brain? This is what happens when we don't have linear part. First of all, I would like to start by giving some definitions and the notion of formal rigidity. And after that, I am going to talk about Poincaré-Dulac and chain theorems and some formal rigidity results for germs without linear part. Then, as the first part, we have definitions and formal rigidity. In what follows, we will take B and W, two germs of real analytic, this is real analytic, or smooth vector fields, with an isolated singularity at the origin in the real plane. In what follows, I am going to denote a germ and any representative in the same way. Then we can take the phase portrait of B, and this phase portrait is a singular foliation by real cubes and will be denoted by FB. This is defined on a neighborhood of the origin in the real plane. And in the same way, we can consider the singular foliation FW. Now we can suppose there is a change of coordinates which maps the foliation FB into the foliation FW. This is, there exists H, a local diffeomorphism, which maps any phase cube of B passing through X, this is X, and into the phase curve of W passing through H of X. This is the phase curve of B passing through X under H is the phase curve passing of W passing through h of x. And then differentiating this expression with respect to t, we obtain an equivalent expression. W is the push forward of E by H multiplied by K. K is a scalar function. And this is the push forward, and the origin under K is non-zero. Then, for example, if we are considering P and W real analytic, then H will be real analytic, and as a consequence, K is real analytic. And in this case, we will say that the foliation FB and the foliation FW are real analytically equivalent. And in a similar way, if we consider B and W smooth vector fields, then H will be smooth and K. And in this case, we will say FB and FW are smoothly equivalent. Then we have a geometric relation which induce equivalence relations of the classes of real analytic and smooth vector fields. But this geometric relation implies a formal relation too, considering the Taylor series of this expression. More specifically, we have the Taylor series of W. This is the Taylor series of W. Is the push forward of the Taylor series of B under H involved multiplied by K involved, where H involved is the Taylor series of H and K involved is the Taylor series of K. But in general, we can consider H an invertible formal transformation and K a formal series with non-zero linear part. And in this case, we have another equivalence relation, and we will say that FB and FW are real formally equivalent. Yes. Then we have the geometric relation implies a formal relation. Now the question is, when could the formal relation imply the geometric relation? If it happens, then we have formal rigidity. Now I would like to talk about Poincaré-Dulac and Chen theorems. Then we have the second section. Second section is formal rigidity. For germs with linear form. In this section, we will consider B with linear part A and L1 and L2 are eigenvalues of A, and we will suppose they are non-zero. Then we have Poincaré-Dulac theorem. It will be the real plane version. And here we have B and W are real analytic, satisfy and satisfy one of the following conditions. L1 over L2 is not a real, a negative real number, or L1 over L2 is a negative irrational number, and in this case, L1 and L2 satisfy the Bruno condition. This is the non-negative linear combinations of L1 and L2 have a control growth, or more specifically, decrease of exponential. Under these conditions, we have the foliation FB and the foliation FW are real formal equivalent if and only the foliation FB and the foliation FW are real analytical equivalent. In this case, these relations consider parametrization. This is in this expression we have P and S are the same, and as a consequence, K is the constant function 1, and here K involved is identically 1. Then for the proof, we can take H involved, an invertible formal transformation realizing the real formal equivalence, and under these conditions we can prove this H is convergent. And now we have Chen theorem. Again, it's the real plane version. And here we will consider B and W smooth germs of smooth vector fields. And L1 and L2 are real hyperbolic. This is the real parts are non-zero. And under these conditions we have these foliations are real formally equivalent if and only if they are smoothly equivalent. Now, again we can consider and again these relations consider parametrization. Now, we can consider again H involved realizing the real formal equivalence. But in this case, by Borel theorem, there exists a smooth realization of H involved. There exists H, a smooth diffeomorphism satisfying its Taylor series is at the origin is H involved. And if we consider the push forward of B under H, this is W plus a flat vector field. Here, flat means that its Taylor series is identically zero. But to prove the Chen theorem, we need this vector field is identically zero. Then Chen theorem is not an immediate consequence of Borel theorem. In fact, in the proof of Chen theorem is constructed a suitable smooth realization of H involved. Then, now I would like to talk about some formal rigidity results for germs without linear part. Here, we will consider a natural number n greater or equal to 2. And we will denote by mu n infinite the class of germs of smooth vector fields satisfying its n-1 jet at the origin is identical to 0, and its n jet at the origin is non-zero. We can consider the class of germs mu n r, which has real analytic germs satisfying the above conditions. Then Laurentiis and I have proved the following results. Here B and W are in the class mu and R, and under generic conditions we have F and FW are real formal equivalent if and only if they are analytically equivalent. And the second is the first result, and the second result is for smooth germs. Here B and W are in mu n infinite, and under certain conditions we have FB and FW are real formally equivalent if and only if they are smoothly equivalent. Now I would like to talk about the conditions of these theorems, and after that, I would like to give the main idea of their proofs. Then we have the conditions for the first theorem, and here we will consider the foliation FB defined on a neighborhood of the origin in the real plane, and then we can consider the complexification of this foliation. We can consider the complexification of B, which is a holomorphic vector field defined on a neighborhood of the origin in C2. This is C2. And this vector field induces a holomorphic foliation, which will be the complexification of FB. And now we can consider the singularization of this foliation, which is a singular foliation defined on a neighborhood of the complex exceptional divisor in the complex matrix band. This is the complex exceptional divisor, and this is the complex matrix band. And this foliation has isolated singularities on the complex exceptional divisor and is mapped by the blow down into the complexification of FB. This foliation will be called the desingularization of the complexification of FB. Now, the first condition is the complex exceptional divisor is an invariant set of this foliation. This is B is non-euclidic. The second condition is this foliation has n plus 1 pairwise different singularities on the complex exceptional divisor, and each of them is linearizable, analytically linearizable, and has two sprite risks. And the last condition is about the holomorphic group of this foliation. We will require this holomorphic group is non-solvable, and this is the last condition. Here, maybe. And then the last condition is this foliation has non-solvable holomorphic group. Now, the conditions for the second theorem are similar. Here, we consider the foliation FB defined on a neighborhood of the origin FB. This is singular foliation defined on a neighborhood of the real exceptional divisor in the real medius band, which has isolated singularities on the real exceptional divisor and is mapped by the blowdown into FB. It will be denoted by, in this way, and is the singularization of FB. And again, the first condition is the real exceptional divisor is an invariant set of this foliation. The second condition is this foliation has K pairwise different singularities on the real sectional divisor, and each of them is smoothly linearizable and has two separations. Here we don't consider saddle nodes. And the last condition is there are not adjacent nodes. This is if we have the real sectional divisors, and for example we have 4 singularities, U1, U2, U3, and U4, and we have a node in U1, then U4 and U2 cannot be nodes because they are adjacent to U1, but we can have a node in U3. And these are all conditions for these results. And now I would like to talk about the main idea of the proofs. Since it's very similar, I only talk about the smooth case. Then, in this case, we have the foliation FB. And foliation FW are formally equivalent. But we can prove without loss of generality that they have the same separatrices. And as a consequence, we have the singularizations have the same singularities in the real exceptional divisor. And moreover, we have U1 here and U1 here. They have the same characteristic number. We have the singularization of FB and the singularization of FW. And the main idea of the proof is to extend the local equivalences given by the linearizations on a neighborhood of the real exceptional divisor. And to make these extensions, we construct a smooth dicritic foliation which allows us to extend the local linearizations and gives us good coordinates together with the singularization of FB and the desingularization of FW. And then we can consider a smooth diffeomorphism defined on a neighborhood of the real section of the bison, which maps the singularization of FB into the singularization of FW. And finally, we prove the blowdown of this diffeomorphism is smooth and maps the foliation FB into the foliation FW. And that's all. Thank you.
Any question?
Can you say something on the condition of the nodes not being adjacent?
Oh, yeah. At this moment, it's necessary to extend the linearizations. Yes, it's a little complicated because it's for example, if we have two nodes adjacent, if we have adjacent two nodes, we have a linearization. It's U1. You have a linearization to be a unique linearization for U1. But for example, you need to extend these linearizations. Then the nodes are very, very bad because the linearization is at this moment impossible to extend.